Okay, everyone, so we're looking at section 2.3 here, how equilibria, which is the plural of equilibrium, how equilibrium responds to volume and temperature changes. Okay, so yesterday we looked at how equilibrium responds to concentration changes. Today we're looking at volume and temperature. So just something to keep in mind, we're going to talk about volume first. So pressure and volume are inversely related. Okay, so sometimes the question will talk about the volume being decreased, but it also might say something about pressure being increased. So just so you have an understanding, when you decrease the amount of volume or space that an equilibrium is happening in, it's the same thing as saying you're increasing the pressure, and then vice versa. If you were to increase the volume that equilibrium is happening in, you are lowering the pressure. Right, and pressure really is just really a measurement of like the number of collisions within a certain force per unit area, right? So like collisions happening within the walls of the container. So equilibrium responds to volume changes by shifting to relieve some of the added pressure or to replace some of the lost pressure. Essentially, how you should think of this is whatever change you make, the shift is going to try and do the opposite, right? So if we increase the pressure of a system, it's going to want to decrease it. If we decrease the pressure of a system, it's going to want to increase it. Okay, so here's an example. So this is a container. Everything in here is a gas, right? So we have blue and yellow gas reactants making a green gas product. So here is our standard pressure in the middle. So this is like the initial equilibrium. And then we can see what's happening where we push down the volume space, right? So we have lower volume, higher pressure. Or moving to the left here where we can see that this piston has been raised, which means that we have a higher volume or a lower pressure. Okay, so when we're looking at what shift is happening, you essentially have to compare the number of gas moles on the reactant side versus the number of gas moles on the product side. Okay, so what I mean by that is, for example, here, I just put the line to separate it. I have two different reactant gases. So this is like I have 2 moles worth of gas on the reactant side versus 1 mole of gas on the product side. So in other words, the reactant side is going to take up twice as much space as a gas compared to the product side. So essentially the equilibrium is going to want to fit in whatever space you are giving it. So let's talk about the one on the right-hand side first, where we are decreasing the volume. So what's going to happen here is it's going to shift to the direction of the equilibrium that is going to occupy the least amount of space. So in this case, it's going to be a shift to the right because remember the product side is occupying less space than the reactant side. So in order to try and decrease the pressure a little bit, it shifts to the direction that will essentially allow it to take up less space, in this case, the product side. On the left side, when we're increasing the volume, it's going to actually cause a shift to the side of the reaction that's going to try to occupy more space. Because what happens is you have a decrease in pressure, so it will shift towards making more particles, so that way the pressure is sort of restored. Obviously not to the point where it was originally, but it restores it to a certain amount, right? More than it was before. So this is going to depend totally on, before we get to that, what type of reaction you have going on, right? So if I have 2A gas plus B AQ and C gas plus 2D gas, right? So when I'm talking about a stress of pressure or volume change, you only look at the gas components. So for this particular one here, I have 2 moles worth of gas on the reactant side. So B would not count towards that because it's not a gas. And on the product side, I have 3 moles worth because I have 2 different components, right? And remember, you look at the coefficients to look at the ratios. So for this particular one, if I were to increase the amount of volume, which means I'm going to decrease the pressure, for this particular reaction, it would actually shift to the right because the product side is going to be occupying more space, right? So it'd be able to fill that space better. If we were to do the opposite, decrease the volume and increase the pressure, right, it would shift towards the reactant side because, of course, the reactants in this particular case is going to be taking up less space. So it's really dependent. Every reaction is going to be different, but you look at the number of gas moles. Okay. All right, so let's take a look at these practice problems. So we have in the system below, if the system below is compressed, okay, in what direction will the equilibrium shift to restore, which direction will the system shift to restore equilibrium? Okay, so let's look right here. We have 2 versus 3. So 2 moles of gas on the reactant side versus 3 on the product side. So if we are compressing, that means that we are increasing the pressure, decreasing the volume, right? We're making it more condensed. So in this particular case, the side of the reaction that's going to take up less space is the reactant side. So in this case, it's going to shift to the left, right? I think that's pretty much all you have to say. So what's going to happen here? Why is it doing this? Right? It's because the reactant side is going to be able to create less pressure with a lower number of moles of gas. Okay. Now, keeping in mind that all of the concentrations, so they're asking how will the concentrations compare to those before and after compression? So even though you are causing a shift to the left, all concentrations will actually increase. So remember, concentration for a gas, you're looking at the partial pressure. So even though you have a shift in the rate, so the reverse reaction rate is going to be going faster, right, to try and condense this down to occupy less space, all of the concentrations are going to be increased because simply what's happening is you have it in less space. So let's say moles per liter, you literally have a smaller volume that you're dealing with. So the number of particles per liter of space is of course going to go up. So all concentrations are going to increase in general, anytime that you are compressing a system. If you are opening up a system and you are giving it more space, in general, all of the concentrations will actually decrease. So you will have a shift, but in terms of concentration, it's going to have a little bit of a different effect than it did in the lesson previous to this. Okay. So here the system is diluted, right? So meaning so here we're dealing with aqueous solutions. So in this case, we're talking about the pressure of the dissolved solutes. Okay, so for example, instead of dealing with empty space with particles within it, right, when we think about with gases, you can talk about pressure in terms of solution, like solubility pressure. It's kind of a different way of thinking of it. Think of it as you have less solvent space. So if you are diluting a solution, and we need a little bit more of a background on this guy. So let's say I have a certain level of concentration, like 1 mole per liter of, I don't know, let's do sodium ions, right? So I have a certain amount that's dissolved in here. So every 1 liter of water, I have 1 mole worth of those ions. If you were to dilute a system, so let's say I'm going to put this in a lot more water, but I'm going to keep the number of moles the same. So let's say instead of 1 liter, so let's say I have 1 mole in 1 liter of solution. If I still have that 1 mole, but now it's in 2 liters of solution, right? Now I have a lower concentration, right? My moles per liter is now less because there's more solvent that's been added. If you are making something more concentrated, that's the opposite of dilution. So dilution, I know you've covered in last year, but obviously we may need a little bit of refresher here. So in this case, it says if you're diluting it, you want to think it's very similar to when you have empty space. So if you have now all of this available space for those ions to float around in, because we're dealing with more solvent area, it's going to shift in the direction that's going to occupy the most space within that solvent, right? So in order to think of it that way is which side will create the higher amount of ions, right? So if you were to condense it down and have less available solvent space, it would shift to the direction that will keep the lower amount of ions present, right? So in this particular case, so now like ignoring all of this, right? I just use those numbers as an example. So hopefully it kind of makes a little bit more sense. So if we were to look here, so we have one ion on the reactant side. So let's just do one versus on the product side, we have 3 ions, right? 3 moles worth of ions. So if we're diluting this space out by adding more solvent, we're going to cause a shift towards the forward reaction, right? Where we're going to have more ions. So this is going to be a shift to the right. Now, in terms of how are the concentrations of all the species going to be impacted, all the concentrations are actually going to decrease. So even though you have a shift to the right, making more product, in general, just like you saw with the number crunching we just did, when you add more solvent, you have less particles per space or per liter of water or whatever it is. So in general, all concentrations will decrease. All concentrations are decreased. Okay, so if you give it more space, you're going to cause a shift, but all the concentrations will decrease. Some more than others, obviously, but in general, they're going to be lower than what they were before. If you were to give it less space, so going back to this one, so the less space, you're going to, in general, have higher concentrations because the per unit area or the volume amount is less, right? So you're going to have just naturally more concentrations, or higher concentrations, I should say. Okay, and example number 3 here, we have the volume of the system below is decreased. So we're lowering the volume, which means an increase in the pressure. So here, I have 2 moles worth of gas compared to 2 moles worth of gas. Will the equilibrium system respond? The answer here is no. And the reason why is because we have equal moles of gas on either side. We have 2 versus 2. So therefore, you're not going to have a shift. No shift will cause a relief in pressure, right? Because remember, the whole purpose of this is if you're increasing the pressure, the equilibrium will shift to try and decrease that pressure increase. Decrease the pressure increase, funny. But anyways, you're trying to do the opposite, right? So if you're increasing pressure, it's going to want to decrease it. So if you have the same number of moles on either side, there's no shift that would be able to decrease the pressure of what was just done to it. Okay. All right, so before we get to this one, I'm going to pause this and we'll do another part.